Okay, if you didn't get the mechanisms graded practice problems for Monday, I have some there. Question today, I want to try and finish up, or we can finish up chapters 7 and 8, SN1, SN2, before we move on to E1s and E2s on Monday. So, do you have any questions about the SN1, SN2?
There was like a practice set on campus, but can we go over like it's like comparing to and choosing which one based off of like the better reading or like how to?
So, was it which chapter 7, 8?
Yeah, but it was just like we just go over like the better reading or than wrong.
Okay.
Relationship.
Sure. So in both cases, the leaving group, if you look at SN1 or SN2, so if you look at SN2, the rate equation bless you. So the leaving group will always play a role in an SN1 or an SN2 reaction going faster. And the reason is because the leaving group, in this case, what I'm calling X, is in the rate equation for both SN1 and SN2. So if you change the leaving group to being better, it's going to speed up both of these reactions. If the leaving group is poorer, it's going to slow down either one of those reactions. So the question is, what makes a good leaving group and what makes a poor leaving group? And so what is the one thing that leaving group ability is based on? Basicity. How? Directly or indirectly? Indirectly. So that means the stronger the base, the poorer the leaving group, the weaker the base, the better the leaving group. So one of the problems if you look, we work up to, is the idea that I could say, for instance, okay, I'll give you a pair of reactions, and I'll say, which one of those two reactions, A or B, goes fastest? And your choice would be either A or B or C, that they have the same rate. So what do we think for this one? A's faster.
So like the polar ability. So if they're like both the same, like that vertically.
So B, I hear. We'll leave the answer at that. Then we'll go back and take a look at it. So A and B, I've got an A and a B. Let's vote. Let's take a minute and vote. And I'll put a D in. So which one of these two is faster, A or B? If you need a card I've got cards up here, extra cards, if you didn't bring yours, so that you can play along. Okay, your choice is A, that A is faster, B is faster, they occur at the same rate, or don't know. Okay, I've got 17 B's, 3 A's, and 1 same rate. Okay. So when we're doing these kinds of problems, and this is going to lead us to something else we just need to go over, the first thing I need to know is what mechanism am I looking at here. Now, I cannot give you mixed mechanisms. I can't give you an SN1 and an SN2 and have you relate those two reactions, okay? Because it's impossible to do that. As an example, if I was to do an SN1 reaction in lab, after next week, we're going to do the SN2 reaction where we have to reflux something for 45 minutes. And so that means we have to heat it and boil it for 45 minutes. That's an SN2 reaction. If I was to do the SN1 reaction, the comparable one, I would put the stuff in a centrifuge tube, cap it, shake it, done. So SN1 occurs a lot faster in that case than SN2, which may seem counterintuitive because you're like, wait, 2 steps is faster than 1? Absolutely. So we can't compare SN1 and SN2. So when I give you 2 reactions, or you see 2 reactions, which one's faster or slower, they have to be the same mechanism. So in this case, what is the mechanism for this reaction? Okay, let's vote again. A, SN2, B, SN1, C, don't know. So what do we think here? Are they both SN2, both SN1, or you don't know? And don't know is perfectly legitimate. If don't know ever gets to the point of being the number one answer, then I know what I need to immediately talk about. Okay, we've got 16 SN2s and 6 SN1s. Okay, what kind of halide do I have here? Primary, secondary, tertiary. Primary. We all agree these are primary? Because if we can't do that, then we need to go back and review that, because without being able to determine primary, secondary, tertiary, we're done. We can't go any further. So these are both primary because the carbon that's attached to the halogen has one other carbon attached, so it's primary. So primary halides can only undergo what reaction? SN2. They can't undergo SN1 because in order to undergo SN1, you would need to form a primary carbocation. Do those exist? Not in this class. So this primaries must go by SN2. Conversely, tertiaries can only go by SN1. So really the secondaries are the issue. What do they do? We'll get to that. But SN1 for primary. So if this is an SN1 mechanism, our next question would be, what's different about these two reactions? What's different about these two reactions is the leaving group. So then we would say, well, which leaving group is better? Then we would have to go to our head and say, what makes a better leaving group? And your head would say basicity inversely. So which one is of Cl minus and of I minus, which one of those is the weaker base? I minus is the weaker base. Because as we go F minus, Cl minus, Br minus, I minus down the periodic table, the basicity decreases. And if you don't remember why that is, it's because going from HF to HCl to HBr to HI, going down the periodic table that way, the acidity does what? It increases. So you increase acidity, you decrease basicity. Okay. So I minus is the weakest base, which makes it the best leaving group. Now, if we talked about nucleophilicity, who would be the best nucleophile of this group? They would be the same. I minus would be the best nucleophile because of it's the most polarizable. So the polarizability comes into play for the nucleophilicity, whereas it's just going down the periodic table, it becomes a weaker base. So leaving group ability is based on basicity inversely. And that's something you have to remember because we're going to use this over and over and over again. It's a basic fundamental concept that we're going to use. Now the next question would actually be then, so I minus is the better leaving group, but then our next question would be, does leaving group ability affect the rate? And we started off by me saying, yes, leaving group ability will always be affecting the rate because it is in the rate equation for both SN2 and for SN1. So when we're looking at reactions, why they go faster or slower, we kind of need to go through that sequence. We need to know the mechanism, we need to know what's different, and we need to know if that difference is important in the rate. And if it is, which of those two would cause the faster reaction. Okay, so for leaving a group ability, I is going to be the best leaving group. And if you remember from a couple of days or last week or sometime, I minus is the best leaving group, but I minus of the halogens is also the best nucleophile, and that leads to kind of an equilibrium if you use iodine, which is why we don't normally. Jillian?
Can you go over a similar process but compare the components of alkenes?
With
Alkenes. I think it's in chapter 8.
With alkenes. You mean like allylic?
I think so.
So, yeah. So let me do one more, and then I'll talk about allylics and benzylics and all of this stuff. So let me give you another problem here. Same kind of problem. Which one of these two reactions goes faster? Okay, so I'll give you a minute to think about it. Discuss if you need to discuss. And then we'll vote. Are we ready to vote? Do we have an answer to vote? Okay. So we are voting for which one is faster, A, B, or they occur at the same rate. Those are your choices. We want everybody playing along. Okay, we ready? All right, let's go ahead and vote. We have 6 A's, 8 B's, 7 C's, and 4, I'm assuming, don't knows. Okay? All right, so since we're all over the board, we could discuss again, but let's go through step by step. You tell me. What would be the mechanism of these two reactions? SN1. Why SN1? Because it's a tertiary halide, too sterically hindered to undergo SN2, most stable carbocation, SN1. All right, what's different about the reaction? What's different about these two reactions? They have different nucleophiles. The nucleophiles are different. Which one's a better nucleophile, fluoride or hydroxide? All right, let's vote on that. Let's vote on which one is a better nucleophile, hydroxide or fluoride, and you do not have the option of saying they are the same. So one of these two is a better nucleophile. Which one is it, fluoride or hydroxide? Which one is a better nucleophile, fluoride, hydroxide? Hydroxide is A, fluoride is B. Okay. We have 8 for hydroxide as a better nucleophile and 13 for fluoride and 1 don't know. Okay, so we need to go back and talk about what makes a better nucleophile. So, what makes a better nucleophile? If the relationship is vertical, what determines Nucleophilicity. Polarizability, if it's vertical. If it's horizontal, what determines nucleophilicity? Basicity, stronger base, stronger nucleophile. Okay, in the upper right-hand corner, we have a periodic table. How does basicity work on the periodic table? Basicity goes right to left, left to right. Right to left, basicity increases. So going from right to left, the basicity increases. So what's the stronger base? The strongest base would be a C minus. Then N minus, then O minus, then F minus. If I dump hydroxide into water, it's going to react with the water to form more hydroxide. If I dump fluoride into water, what happens? It's in an equilibrium, right? It partially reacts with the water. So that makes hydroxide a stronger base. Okay, so this is then the stronger base. Now, does that make sense? Since the majority had fluoride, HF is a stronger acid than water, but that means its conjugate base is weaker. So on the periodic table, if we go from left to right, acidity increases. But if we go from right to left, basicity increases. Right? Just the different thing. Okay? All right, so where are we at? We're at an SN1 mechanism. The nucleophile is different, and hydroxide is the stronger nucleophile. My question number 4. Does the strength of the nucleophile affect the rate of an SN1 reaction? I see some head shaking. Is the nucleophile in the rate equation for an SN1 reaction? No. What was the rate determining step in SN1? Breaking the carbon-halogen bond. So in this case, yes, hydroxide is a stronger nucleophile, but in an SN1 reaction, does it matter? No. So what does that mean? That means that those two reactions occur at the same rate. So for an SN1 reaction, changing the strength of the nucleophile doesn't matter because it's not in the rate determining step. Now, changing the strength or the betterness of the leaving group does because it's in the rate determining step. So for SN1 reactions, changing the nucleophile strength doesn't matter. Does that make sense? If it doesn't... So in these kinds of reactions that you'll probably see on the exam, not next week, but the Monday after, right, we'll let Halloween get out of the way. I taught at OU one time. I think I gave an exam the Friday before, maybe it was a Monday after Halloween weekend, which down there is a national holiday. And they were like, you can't do that. And I'm like, really? Well, it's Halloween. Well, I wasn't aware of OU's Halloween national knownness. I'm like, I did it anyway. So we'll let it get out of the way here. But does that make sense? So as you're going through the steps, the first thing you got to do is identify mechanism, what's different, and then you could even ask the question up front, does that difference make a difference? Does that difference affect the rate? And if the answer is no, then they're the same. and then go to which one is better, which one's going to make the reaction faster. Okay? And that involves that we really understand all of the mechanisms and those 4 characteristics that we went over. I still have one more thing to do from the other day, the Hammonds Postulate. So does that kind of make sense? I don't know if that was the exact question from the book, but these are the kinds of questions, and there'll be some practice problems I'll put in the folder for today where I ask you to do this. And the things I can change are the leaving group, I can change the structure of the alkyl halide, I can change the solvent, which we probably need to I need to ask you a question about the solvent. Okay. But does this make sense? Now, what about these allylic and benzylic systems? So in one of my PowerPoint slides, it's in my video, I have these. So let me talk about terminology. When you have a halogen directly attached to the double bond, that is called a vinyl halide. Okay. And this specific molecule is called vinyl chloride. Now, if you've heard, the vinyl term, which used to be more popular with the record albums, which apparently have come back into vogue, although the sound quality is not that good. I now remember why I moved to CDs, and who buys CDs anymore, except me. So I still have a CD player in my car, but the sound quality of the albums is not. And I still have a big stereo system from when I was in college. So, that you can now buy at the Goodwill store for like a tenth of the cost. That's vinyl. That vinyl is made of vinyl chloride that we make a polymer out of. That's PVC. PVC is also the white tubing that's used in plumbing. So that's where the vinyl term comes into play. So I mean, it has a different context in English as opposed to what it means in chemistry. It means your halogen's directly attached to your double bond. Vinyl things do not undergo SN1, and they do not undergo SN2 reactions. So anything that has a halogen attached to a double bond will not undergo SN1. It will not undergo SN2 for various reasons, which I won't get into, other than they don't react. Add an additional carbon, though, and we have a totally different ball game. Because if you add an additional CH2 to that, you have what's called an allylic halide. So the allylic carbon, which we'll talk about in great detail next semester, the allylic carbon is the carbon attached to the double bond. The vinyl carbons are the double bonded carbons. So allylic halides will actually undergo SN1 very quickly. And the reason for that is because they form stable carbocations. So even if I take this allylic chloride and I break the carbon-chlorine bond, I form a CH2 with the plus charge. Now, before anybody says, that's a primary carbocation, you can't write that. Number one, I can pretty much do anything I want because I'm in charge. But number two, that actually is stable because it's not just a primary carbocation. Because if I take this pair of electrons and I move it over here, I can actually then write a second resonance structure where the positive charge would move to the left carbon and the double bond would move between the middle and right carbons. And the rule from first couple weeks of class are the more resonance structures you can draw, the more stable the molecule. And so in this case, being able to draw these two resonance structures makes that primary allylic, more stable than a primary carbocation, and so that is stable.
Would you consider that to be a secondary carbocation ion then because of the double bond? Or would you...
No, it's still primary because that carbon is attached to one other carbon. So the double bond doesn't matter for secondary, primary, secondary, tertiary. It's treated as if it was a single carbon because it is a single carbon. So this is what I would call a primary allylic carbocation. Now, where I would place this on the ranking list, I always think of these things as having probably stability close to a tertiary carbocation, but ranking them is sometimes kind of difficult. But it is stable. And it's stable because it has two resonance structures. If I made that a secondary carbocation, no problem, it's very stable. I would put that up there with tertiary, maybe even more stable than a tertiary carbocation. Okay. So when they talked about allylics, allylics can undergo both SN1 and SN2. SN2 because they're primary, SN1 because they can form a stable carbocation. So for allylic systems, that's what they're talking about. We're not going to really do anything with allylic systems until next semester. But they really do, in Top Hat, they really do like to foreshadow a lot of stuff. The problem is they just foreshadow it so far in advance that by the time we get there, we might as well just talk about it again as opposed to saying, do you remember back then? Because the answer is probably no. Because it was a long time ago. Long time could be last week. So these are stable carbocations. Now the one that's gotten me kind of in trouble recently is the idea that you can have a similar type system with the carbon that's attached to a benzene ring. So if we erase the benzene ring, we would have an allylic system. The carbon that's attached to the benzene ring is what's called a benzylic carbocation. So benzylic carbocations are actually very stable as well because they have the double bonds in the benzene ring. And next semester we'll write all those resonance structures out. But benzylic carbocations are also stable. Even this one would form because it's a primary benzylic carbocation. And what I mean by getting myself in trouble is that Brian is working on a research project here where we were trying to determine which one is more stable, the benzylic carbocation or a tertiary carbocation that's right next to it. And in class, I would have said, next semester, I would have said, oh, well, the benzylic carbocation is definitely more stable than the tertiary. And I would be dead wrong, because what we're finding is that the tertiary carbocation is more stable than the benzylic one through reactions that we'll talk about upcoming, which is confusing me because I'm not quite sure why that is, and I can't find anybody who has a definitive answer for that. And when we first found this, he was like, well, everything you taught me in Organic 2 last year, I don't believe now because this is wrong. And I said, well, I agree with you that it appears as though that's not the easy answer, but we're still trying to figure out why that's the case. But it is the case. So it's one of those things that once we figure that out, when I give a talk in front of a whole bunch of other organic people, I'm going to start with like, which one of these is more stable? And then they're going to argue. There's going to be fist fights. And then I'm going to say, here's what we found. So that my ranking system has come into question when I've just ranked these things on paper. But benzylic systems are also very stable. Apparently not as stable as the tertiary system, at least in this one. So that's why they put those in the book. Benzylic carbons, if I go back here, this benzylic still being primary will undergo SN2. So benzylic and allylics will undergo SN2, and they will also undergo SN1. Because even though the primary systems, they're primary with resonance structures, which makes them more stable. So that's why the book has included them, is because they're foreshadowing the idea that these carbocations can have resonance structures. We'll get to that in great detail next semester. Okay. So that was what those ones were about. The rearrangements. Let's hold off on rearrangements for the moment. I always debate whether to include rearrangements right now or not, and maybe we will hold off on those for the moment. We will talk about them before the end of the semester, but I don't know that right now is where I want to talk about them. Okay. Or maybe I do. We'll talk about them in maybe in E1s. Because what I still want to do is talk about solvent effects to make sure we're all on the same page there. Okay. Has everybody taken a look at the solvent effects in the book or watched the video? All right, I feel obligated to test that. So, CH3OH. Polar solvent? Yes. All of the solvents that we do SN1 and SN2 reactions have to be polar because I'm dealing with ions. And the only way to get the ions to dissolve is to use a polar solvent. But there are two classifications of polar solvents. There are protic solvents and there are aprotic solvents. And then I've confused the issue by introducing the idea that a protic solvent is a hydroxylic solvent, and an aprotic solvent is also called a non-hydroxylic solvent, which isn't really confusing because I find those terms to be much more descriptive of what these protic and aprotic solvents are. And if you dealt with these solvents and things, there's a certain researcher who promotes this. It was happened to be somebody who I did some PhD research using their stuff, so that's why I like the term. But protic, aprotic, methanol, what kind of solvent is that? Protic, aprotic, hydroxylic, non-hydroxylic? Which one is it? Let's vote. A, B, C. Aprotic, B aprotic, C, don't know. Okay? Those are your choices. Whoops. Okay, we've got 19 protics. So this is a protic or hydroxylic solvents. Again, the hydroxylic means it has an OH group. Protic means that it has a proton that could be lost. And so alcohol and water are typical protic. These are our typical protic solvents. Why? Because they have hydrogens that can be lost, which is a misnomer because some of the aprotic solvents also have hydrogens that you can deprotonate. but that's why I prefer the hydroxylic, non-hydroxylic, but nobody's written a book like that. Although I could actually put it in this book, which I haven't. You've seen that my edits have gone away because I haven't had time to go in and edit it. So this is a protic solvent. Things that are aprotic are going to be things like acetone and the sulfur equivalent, which is called dimethyl sulfoxide, or DMSO. You may have heard DMSO. It is used sometimes by people as a topical anesthetic, or if they have muscle soreness, they will rub DMSO on their soreness, because DMSO goes directly into your bloodstream. Have I had DMSO go directly into my bloodstream? Yes, it tastes garlicky. But I would not use that as a medicine, because I don't know what's in the DMSO that people are using. Because whatever's in there is also going into my bloodstream. So occasionally I have some spill on me and I'm not wearing gloves, which I should be wearing gloves. But that's what it tastes like. If you're driving in the hills of West Virginia and you see DMSO sold here, which I remember seeing one time, I wouldn't stop there, because I don't know. They probably don't have a nice still to distill it and make it nice and pure. So that's an aprotic solvent. The other one they like to use a lot in the book is DMF. And DMF is dimethylformamide, which has two methyl groups attached to the nitrogen of the one carbon amide. And so formamide means one carbon amide, and the dimethyl, there's only two places to put methyls, and that's on the nitrogen. So these are all examples of aprotic polar solvents. Basically, anything that's not water and not alcohol is aprotic. So the question is, which solvent does SN1 go faster in? Which reaction, or what solvent does SN2 go faster in? Okay. And so, for instance, if I said for this, if I took a tertiary halide and I said, okay, tertiary butyl chloride plus hydroxide in acetone, or tertiary butyl chloride plus hydroxide in water, which reaction would go faster? In order to answer that question, I would need to determine mechanism. So the mechanism for these two reactions is SN1, because it's a tertiary halide. What's different about these reactions? The solvent. Does the solvent play a role? Yes. Which way? So which solvent speeds up or slows down an SN1 mechanism? Which one makes the reaction go faster? Protic? Are we agreed? So this reaction would go faster because the protic solvent speeds up the SN1 reaction. I'm going to assume that there is one person out there who might be going, why? I could refer you to at least two videos, but I will make a third here. The rate determining step in the reaction is the dissociation of the carbon-chlorine bond. Now, what protic solvents, the advantage that protic solvents have, and the role that protic solvents have, and this is a question of, does the protic solvent increase or decrease the rate of the reaction? The aprotic solvents, it's just a question of what does the protic solvent do, and then the aprotic makes it either go faster or slower because it's not protic. Protic solvents have the ability to solvate ions really well because they can solvate through either the hydrogen or the oxygen being slightly positive, or in this case, the oxygen being slightly negative. So protic solvents solvate ions better than aprotic solvents. And that's the key. So in an SN1 reaction, by solvating these ions, what am I doing? I am making the products more stable. So by using a protic solvent, I am making the products more stable. What does that do to the rate of the reaction? It's going to make the reaction faster. Similar to when we talked about taking an acid and it dissociating into H plus A minus, how can I make this a stronger acid? Make A minus more stable. So if I make the products more stable, the reaction is going to occur faster. And so protic solvents will increase the rate of SN1 reactions. And they will be faster than the aprotic solvents. So it's not that aprotic solvents make the reaction go faster or slower. It's just that their rate is now slower than the protics because the protics solvate the ions better. So in this case, protic solvents are good. They make the reaction go faster because they stabilize the products. What happens in an SN2 reaction? In an SN2 reaction, I've got this nucleophile trying to get to this carbon to kick off the leaving group. What does the protic solvent do then? It solvates the nucleophile really well. So now the nucleophile is in a position where it's got to drag all the solvent with it. And then when it gets over here to this carbon, it's got to kick all that solvent off in order to react. So in this case, really good solvation is bad, meaning that it slows down the reaction. So protic solvents, then, that's really what we have to remember. For protic solvents, if you have an SN1 mechanism, it will cause the SN1 reaction to go faster. But for SN2, because it solvates the reactants, it makes those go slower. And then what about the aprotics? They're the opposite. But the aprotics really, you don't look at them as doing anything. It's just they're not doing what the protic solvent is. So it's as straightforward as that. Protic solvents solvate better. SN2, that slows down the reaction. SN1, it speeds it up. Does that make sense? Okay. Now for Monday, I'm gonna move the. I don't think I put any videos. I will do that today. I'm also, I think, 5, 6, 7 questions behind on Piazza. National Chemistry Week, thank God, is over. Today is the end of National Chemistry Week, because National Chemistry Week has been very hectic, including the bazillion scoops of ice cream from last night. That's the first time they've done this with a department. So I don't know. Apparently it was the lines were as long as the mac and cheese lines, so I think that's successful. But now I can get back to doing my job. So if you have any questions, put them on Piazza. I will clean all those up at the end of the day. I will put in Monday's folder a video on E1, and we can talk about E1. Anything left from here, we can talk about on Monday, or put it up on Piazza, and I will go through answers there as well. Okay, that's due on Monday, so if you have any questions about the mechanisms, shoot me an email or put it up on Piazza as well.